Hey folks, welcome to this episode on molar enthalpy calculations. So recall what a molar enthalpy is. It's just a way of expressing enthalpy in a more standardized way. So when we look at this reaction, again, we've seen this before when we have hydrogen reacting with oxygen gas to produce water gas or steam, whatever you want to call it, vapor, we produce 485 kilojoules. We know it's produced because it's on the right side of the equation, which means that it's made along with the H2O. Now, if we were to put this out by itself, we would put this as delta H is equal to negative 485 kilojoules. Okay. Now, what if we wanted to know how much energy is released for every mole of water produced? Because here we produce 2. What we would do is we take this value over here and divide it by the 2 moles of water that were produced. Remember what a molar enthalpy is. It also has a specific definition attached to it. And so the enthalpy of formation is the amount of energy released or gained, or just in general, the energy change for every mole of product produced. So in this case, we have 2. We want to get it down to 1. So to get it down to 1, we divide it by 2, and we get 242.5 kilojoules. Kilojoules there. Now, if we were to express this by itself, we would have delta H, and we would show F over here to show that it is a molar enthalpy, and specifically the molar enthalpy of formation. We would show that it's negative because it's being produced 242.5 kilojoules per mole. Now, per mole of what? Well, the F over here tells us per mole of what? Per mole of water being produced because it is a formation reaction. So again, this molar enthalpy is expressed in kilojoules per mole. It has this general formula of delta Hx, and that x is replaced depending on what we're actually looking at. And it's a good way of standardizing our calculations. So what you could probably figure out is that to get our delta Hx, in this case, in the previous case, we looked at delta Hf, we took our enthalpy, our delta H, and we divided it by moles. Well, look at that. If we kind of rearrange this formula over here and we generalized, what we get is we get delta Hx is equal to delta H, and if we want to get rid of this fraction, we can put this mole right beside this expression of delta Hx. And another way of expressing mole is just by writing N. So by putting that together, we get this equation right over here. And this is an equation that we're going to be using quite a bit. So the enthalpy change, the total enthalpy, is equal to the moles multiplied by the specific molar enthalpy of whatever we're looking at. Now, if we think about it, this is as let's think about energy as money. Okay, and if, let's say, for example, we were going to the store and we had a box of chocolates, okay, so chocolate bars. And in this box of chocolate that contains chocolate bars, we have a lot of different chocolate bars here. Okay, they're all the same, but we have a number of them. And let's say, for example, you as a seller were retailing these chocolate bars. Each one of these little chocolate bars here costs $1 per bar. Okay, this would be our molar enthalpy. Okay, this is what we'd be calling our molar enthalpy because there's a certain amount of money, in this case money is equal to energy, there's a certain amount of energy for every single bar. That would be like our kilojoules per mole. Now, let's say, for example, we couldn't buy individual chocolate bars, we could only buy the whole box. The question is, how much money will we have to spend? And that would be our delta H. Now, to figure that out, it's actually kind of simple. We know what the price per bar is. It's whatever, in this case, $1 per bar. And we know how many chocolate bars there are in this box. There are 12 bars. Okay? So how do we figure out how much money we're going to spend? Well, we would take the number of bars, multiply it by the ratio, $1 per bar, and we have 12 bars. Our bars would cancel out, and we would get $12. That would be our delta H. That's how much money we would spend. In this case, if we wanted to actually make it even more, it would be negative 12 because we would be expending, we would be producing that amount of money for the seller. Okay? And so in this case, that number is equal to our delta H. N is how many chocolate bars. Our delta Hx is the price per bar, in this case the kilojoules per mole, how many moles. And if we multiply those, we get the total amount of energy change. Now, how does this really help us? Well, if we know how much energy per mole is being created, and we know how many moles are created in the example of a formation reaction, if we wanted to look at that, then we could figure out how much energy would be produced altogether. If we had 1 mole produced 10 kilojoules of energy, well, to figure out what our delta H would be, to take that 10 kilojoules of energy divided by the 1 mole, 10 kilojoules divided by 1 mole, and we would get 10 kilojoules per mole. Now, let's say, for example, we wanted to know how much energy would be produced if we formed 20 moles. Well, since we already know our delta Hx for this reaction, we could just take our 20 moles and multiply them by 10 kilojoules per mole, and we would get our answer of 200 kilojoules. Okay, so this value, delta Hx, is actually a very useful value because once we know this value, we can just multiply it by any moles, and we can figure out the total amount of enthalpy. Now, we also, if you were kind of listening over there, you'd also see that we just use this equation in another way as well. We actually use this equation to determine the molar enthalpy. We said we had 10 kilojoules, and if we know that we had 1 mole, we can rearrange this formula to figure out our actual molar enthalpy. So we could to find delta Hx, we could tell delta H divided by N, and we can find that specific molar enthalpy. So let's look at an example here. Here we have an example that says a common refrigerant, Freon 12, the molar mass of 120.91 grams per mole, is alternately vaporized in tubes inside a refrigerator, absorbing heat, and then condensing with tubes outside the refrigerator, releasing that heat. So this results in energy being transferred from the inside to the outside of the refrigerator. The molar enthalpy of vaporization for the refrigerator is 34.99 kilojoules per mole. If 500 grams of the refrigerant is vaporized, what is the expected enthalpy change? Okay, well, one thing that we already know is our molar enthalpy of vaporization. So we actually know our delta Hx. Now, in this case, the delta Hx, or the delta H, is not actually just delta Hx. We know that it's going to be delta H of vaporization, VAP. And this is going to be 34.99 kilojoules per mole. Again, this is a molar enthalpy because it's kilojoules per mole. Now, the question is, what is the expected enthalpy change? So what the question is asking us for is delta H, not delta Hx or delta Hf or C, whatever in that case. It's looking for delta H. So I'm looking for delta H because it's saying the enthalpy change, not enthalpy per mole, but enthalpy change. And I have my molar enthalpy. How do I get from here to here? Well, remember our equation is going to be delta H is equal to N delta Hx. Well, I have delta Hx, in this case that is delta H of vaporization. And to get here, I need to know my N. Remember, N refers to moles. Moles of what? Well, in this case, it's talking about 500 grams of the refrigerant. The refrigerant is the Freon 12. How can I get moles from 500 grams? Think about it. Think about it. There's our molar mass. So if we take, to find moles, we take our amount, we take 500.0 grams, and if we divide it by the molar mass, which is 120.91 grams per mole, and what we get is we get 4.13531 mole. Okay, so that's how many mole of refrigerant I have. So now I have my molar enthalpy. I have my amount of moles. I just have to multiply the two and get delta H. So I'm going to do that. So my N is 4.13531 mole multiplied by 34.99 kilojoules per mole. My moles cancel out. I'm left with kilojoules. And my answer is going to be 144.7 kilojoules. And 4 significant figures there. Okay? I have 4 here. I have 4 here. So I have 4 in my final. So that is my delta H. And this is going to be positive because all of our other things are positive. All right, let's take a look at this one over here. It says the molar enthalpy of combustion of pentane is 3,509.0 kilojoules per mole. So what that means is that that's the energy change for every mole of pentane. In this case, pentane is a liquid. It reacts in a stoichiometric ratio of 8 oxygens to produce 5 CO2 and 6 H2O. And in this case, that is 3,509.0 kilojoules. So what we can see here is, again, this value is our specific, or our molar enthalpy. We can see that this amount is produced with every 1 mole of pentane being burned. So this is our delta HC specifically, because it's talking about combustion. Okay? Now, because it's being put onto the product side, that means it's being produced. That means that heat is being lost. So 3509.0 kilojoules per mole is our molar enthalpy of combustion. Now the question is, if 2 moles of pentane are combusted, what is the enthalpy change associated with this? Well, what that means is that if we just kind of draw it out over here, we have our stoichiometric ratios over here. So what we're trying to say is that if we had 2 here, 16 oxygens, 10 carbon dioxide, and 12 H2O, how did we get from here to here? Well, simply, we just multiplied all the coefficients by 2. The same thing happens with the energy, because remember that if 1 mole of this burning produces this much amount of energy, logic should dictate if I have twice as much, I should produce twice as much amount of energy. And so is the case. Now, the equation that we use to do that is delta H is equal to N delta H X. In this case, delta HX is actually C because it's combustion. So we have 2 mole there multiplied by negative 3509.0 kilojoules per mole. And what we get is negative 7018.0 kilojoules. So again, this value of negative means that it's lost, so that means it's going to be on the product side, and we expect it to be twice as much, so here we're going to have 7018.0 kilojoules of energy being produced. So here we have a reaction of magnesium and oxygen producing magnesium oxide with the delta H of negative 1200 kilojoules. So again, that negative means that it's being produced. And so the question, there's 2 questions here. It says calculate the enthalpy of combustion for magnesium. Okay, so it's asking you to calculate the molar enthalpy, meaning that kilojoules per mole, and combustion. Now remember what the definition for combustion is in terms of molar enthalpy. It's the amount of energy produced or absorbed, the energy change, when 1 mole of substance is burned in oxygen. Okay, so again, the substance that in this case is being burned is our magnesium. So in this case, when 2 moles of magnesium is being burned, this is how much energy is going to be released in this case. Second question is that says that if we have 0.600 grams of magnesium burned, calculate the amount of heat absorbed by the surroundings. Okay, so try to do these 2 questions. Pause the video now, spend some time with it, write something down, and we'll come back with the answers shortly. Alright, so welcome back. It says calculate the enthalpy of combustion for magnesium. So what we're looking for is delta HC. And if we rearrange the equation, we get delta H over N. Now, in this case, we actually have delta H already. It's given to us over here. So our delta H, we're going to put that in there, is negative 1200 kilojoules. Now, we need to figure out what's our N value. Now, this value over here, the amount of energy that is produced, is based on this equation over here. And you can see that there are 2 mole of magnesium being burned. So that's going to be our N value, is 2 mole. So if we do this out, what we will get is we will get negative 600 kilojoules per mole, as you can see by the units over here. That's it. All right, next question. Now this one seems a little bit harder because all we're given is 0.600 grams of magnesium that's being burnt. It's asking us to figure out how much heat is being absorbed by the surroundings. Well, to do this, what we're trying to look for is we're trying to look for our delta H. But we're not given moles, and we're not given the enthalpy of combustion. Well, actually, we are. Because remember, the last question we did is we determined what the delta HC for magnesium being burnt is, and it was equal to negative 600 kilojoules per mole. So we can use that value. Now, if you weren't given that value, you could calculate it as we see here. We're still given our delta H. We know that we have 2 moles, and we could figure that would be negative 600 kilojoules per mole. So that answers one thing. Okay, because remember delta H is equal to N delta H, in this case C. So we have our delta HC, however we don't have our N. Well, again, if you look at this a little bit more, you'll see that we have a certain value for the amount of magnesium that's being burned. To take this amount and to get it into moles, we just divide by the molar mass of magnesium. So let's do that. We have 0.600 gram, and we divide by the molar mass of magnesium, which is 24.31 grams per mole. Our grams will cancel out, and we'll be left with 0.024681 mole. Okay, so that's our N value. So to figure out our delta H is simply N times delta HC, so 0.024681 mole multiplied by negative 600 kilojoules per mole. Now in this case our moles cancel out, and we are left with negative 14.8086 kilojoules. So what this is this is showing us that magnesium, the enthalpy of magnesium, so remember enthalpy is the total amount of potential and kinetic energy. The enthalpy of magnesium is decreasing. Okay, it's decreasing, it's being lost. Some of the enthalpy within the magnesium here is being lost as heat. You can see that by the negative. So if this is being lost by the magnesium, where is this going to go to? Well, if it's being lost by magnesium, it's going to go into the surroundings. So remember what our equation was a few lessons back, that delta H is equal to the negative Q of the surroundings. So if magnesium lost this much amount of heat, that means the surrounding must be able to pick it up. So in this case, the heat absorbed by the surroundings is just the negative of the delta H, which means that it absorbs 14.8086 kilojoules. Okay, now in this case we had two significant figures initially and three significant figures here. So we're going to keep it to two significant figures, and we're going to call this plus 15 kilojoules. Okay, so again, just to recap here, we figured out what our delta HC was from the previous question. We figured out our moles by taking the amount of magnesium divided by the molar mass. We multiplied the two, and we figured out that the magnesium would lose negative 14.8086 kilojoules in heat. So if magnesium was to lose this, remember that the system and the surroundings are right beside each other. So whatever the system loses will be picked up by the surroundings, shown by this equation here, delta H is equal to negative Q of surroundings, and that means that the surroundings picks up 15 kilojoules of heat. All right, here's another practice question here. So we have methane burning in oxygen to produce carbon dioxide and water. So there's three parts to this. What is the enthalpy change when 50 grams of methane undergoes combustion? Number two, what is the enthalpy change per mole of O2 consumed, CO2 produced, and H2O produced? And number three, determine the mass of oxygen consumed if the total enthalpy change is negative 2.50 times 10 to the negative 2 kilojoules. Now, there's one part here that you will have to try to figure out. And if you have the data tables that were provided by me, you will be able to figure this out. So again, this is asking us for our delta H, which means we need to find N, and we also need to find delta HC. Why delta HC? Because methane is undergoing combustion. Now, if you look at your data tables, you will find this value for delta HC. And so again, this brings up another good point. If the delta HC or delta HF is not provided to you in the question, always go back to your data booklets and you'll find the value over there. All right, so pause the video, break out those data booklets, find that value, and complete the questions. We'll be back with the answers. All right, so you should have been able to find it in the data booklets. The delta HC for the combustion of methane is negative 890 kilojoules per mole. So to figure out what the enthalpy change is, again, delta H is going to be equal to N delta H, in this case C. We have to figure out how many moles we're going to be burning. So we have 50.0 grams, and we divide that by the molar mass of methane, which is 16.05 grams per mole. Our grams cancel out, and we are left with 3.11526 mole. So by taking our 3.11526 mole and multiplying it by the negative 890 kilojoules per mole. Our moles cancel out, and what we're left with is negative 2.77 times 10 to the power of 3 kilojoules. And that is our delta H. Okay, so what has happened is that our enthalpy change has been negative 2.77 times 10 to the 3 kilojoules. So that is a big number. But again, this is being lost. So the system is losing some heat, which means the surroundings are going to pick it up. All right, to solve this number 2 question, what is the enthalpy change per mole of O2 consumed, CO2 produced, and H2O produced? Well, the best thing to do is start off with something that you know. Now, the thing that you know is delta HC for methane, and that's equal to negative 890 kilojoules per mole. Now, in this case, what we look at is that if we look at O2, CO2, and H2O, they are all related somehow to CH4 using our stoichiometry. Okay, so it's a 1 to 2 to 1 to 2 ratio. So what that means is that they are all related based on these coefficients. Now, the first thing I can do is I can convert this value of CH4 into an overall just enthalpy, and I can do that by looking at using this equation. Delta H is equal to N delta HC. So if I multiplied the molar enthalpy of combustion for methane, multiplied the number of moles that it's being consumed, that is being combusted, I can find a general delta H for that. And then, once I find that general delta H, I can use that to calculate all the other enthalpies here. So for every 1 mole of CH4 burned, negative 890 kilojoules kilojoules of energy is being released. So that means that my delta H is negative 890 kilojoules. Okay? So that's a very simple calculation, and I did that just to show you how this actually works. So I'm finding the delta H for this reaction, okay, based on the 1 mole that's being consumed here. So if negative 890 kilojoules is being released for 1 mole of this being consumed, then this value is also related to this, this, and this in the same stoichiometric ratio. So to find the delta H, in this case R, because we're not talking about combustion anymore, it's just we're focusing on something else. We'll look at the oxygen. It's going to be equal to the delta H over the N. Now the delta H is going to be equal to negative 890 kilojoules, and the amount of moles that is being burnt is 2 mole, and so the delta HR for the oxygen is going to be negative 445 kilojoules per mole. Okay, so if I was to look at this enthalpy change altogether, which is negative 890 kilojoules, if I wanted to look at how much energy is being released for every mole of oxygen consumed, I get 445. So now let's look at my delta HR for CO2. That's my delta H of the reaction divided by the N's of CO2. So my delta H of the reaction hasn't changed, kilojoules. But in this case, I only have 1 mole of CO2 produced. So I'm going to divide by 1 mole. And my value for delta H R in this case is negative 890 kilojoules per mole. Okay, so again, I know that 890 kilojoules are being released when this 1 mole of CH4 is being burned. So how much is being formed when 1 mole of CO2 is being formed? Okay, so again, this and this is related to this based on these stoichiometric ratios. And you probably guessed it, if I wanted to do the same thing for water, delta HR, I would take my overall delta H divided by the moles of water. I get negative 890 kilojoules divided by the 2 moles of water being produced, and I would get the same value as oxygen, negative 445 kilojoules per mole. Okay, so for when 2 moles of water are being produced, I will also produce 445 kilojoules of energy for every mole of the water actually being produced. And number 3, it says determine the mass of oxygen consumed if the total enthalpy change is negative 2.05 times 10 to the 2 kilojoules. Okay, so it's asking us about mass of oxygen. Now, the only way we can find mass of oxygen is by first finding moles. Well, what equation has enthalpy, moles, and we know the molar enthalpy before from our previous things. How do we figure this all out? Well, we have this equation here. Delta H is equal to N delta H, in this case, C. Now in this case, using delta HC would not be the best option because we're not looking at the amount of methane consumed, aka combusted, we're looking at the amount of oxygen being consumed. So instead of using C, what we're going to use, let me just erase this here, is the more generic term, and that would be, just get this back, that would be delta HR. Okay? So I know if I rearrange my equation, I get N is going to be equal to delta H over delta HR. Now my delta H is given to me by the equation here. It's going to be negative 2.50 times 10 to the 2 kilojoules. And my delta HR is not combustion. It's actually the molar enthalpy that we found for oxygen before. So if you go back, you'd find that your delta H for oxygen is negative 445 kilojoules per mole. Okay, so go ahead and do this calculation. And what you should get is the negatives cancel out, and you'll get 0.561797, and what you'll be left with is mole. Okay? And this is the amount of oxygen that we have in terms of mole. Now to get mole into mass, we multiply by the molar mass, which is 32.00 grams per mole. And your answer should be 17.9775 grams. Now if we look at this, we have three significant figures, so what we'll get is 18.0 grams. So 18.0 grams of oxygen are consumed when you have an enthalpy change of negative 2.50 times 10 to the 2 kilojoules. Alright folks, thanks very much for watching. See you next time.